Okay, so hello everyone. We will continue with the second speaker of today. We have the honor and pleasure to have with us Professor Alexandre Seuret from the University of Seville. He obtained his PhD in automatic control from the École Centrale de Lille in France and the University of Science and Technology of Lille in 2006. In the next 2 years, he held 1 year postdoctoral position at the University of Leicester in the UK and the Royal Institute of Technology in Sweden. Then, for 4 years, he joined the Centre National de la Lab in Grenoble and at Laboratoire d'Analyse et d'Architecture des Systèmes in Toulouse for the next 10 years. Recently, since 2022, he has been a researcher at the University of Seville. We can say that his research interests include time delay, sample data, and networked control systems, stability and control of systems governed by PDEs, hybrid dynamical systems, and multi-agent and distributed control and estimation. Thank you very much, Alexandre, for having accepted our invitation. Go ahead. Thank you.
Okay, so thank you very much for this invitation. So it's an honor to be in front of you. I must say that I'm a bit impressed because I do not have the habit to present my work in front of mathematicians. So I hope that it will be well received. So as I said, I'm not a mathematician. I'm coming from control. And I turn myself a little bit into the world of PDE and infinite dimensional systems. And so this is like my presentation will be somehow a kind of summary of all what I did in this topic. Okay, so as you said, sorry. So this is just a brief overview of my CV. So I did my PhD I received my PhD in 2006 from the École Centrale de Lille in France, where I started working on time delay system, sample data control, and observation. Then I did 2 years of postdoc. The first year in Leicester University, where I start working in additional area in control, which is called slide remote control. And during my second year at KTH, I worked in addition to the previous stuff, I worked on a multi-agent system and what is called distributed consensus algorithms. And starting from 2008, I have been a associate researcher at CNRS, first as an associate professor at GIPSA when I started working on distributed formation control for multi-agent systems and a fleet of autonomous vehicles. And then I moved to Toulouse when I start working on what is called hybrid dynamical systems. These are class of systems where you have both continuous and discrete time dynamics, but in the finite dimensional case. And I also started working in infinite dimensional systems. And so more recently, I have been appointed as a full CNRS researcher at last when I start working on another class of hybrid system, which is helpful to represent power converters or problems of biology, where you have some switch dynamics with some terms that make the dynamic switched. And since 2002, I have been investigador distinguido en la Universidad de Sevilla, where I have been starting working on data-driven control, spacecraft rendezvous, and control of microgrids. So this is just like a big picture of what I have been doing, and this is a problem that I'm addressing. So it's a typical problem in control, where you have a plant that is to be controlled and optimized. And your objective is based on the information from sensors. You want to design a control law that will be implemented into actuators, and you want to design this control law such that the closed loop system is suitably stabilized, which means that it has the best performance or the desired performance that you want. But if you look at how this kind of loop are implemented nowadays, you have some what is called digital channels that are appear in the links between each of these box, and you end up with something that has been called a network control system, where the objective is to control a system through a network. And the basic problem that you are dealing with is that the information that are going through the network is deteriorate. So you need to take into account this issue. That is that the X hat that you are using to design the control or to be implemented in your controller is not exactly the real information on your system. And so this is something that we have called in Toulouse control with limited information. And again, the objective is the same, is to design robust control law, but in addition to classical robustness respect to what you are, what is a machinery and uncertainties, you want to have robustness with respect to unreliable and constrained communication links. Okay, so just to tell you a bit of what I do mean by communication limited information. So the first thing is delay. So when you have some quantities that are moved from one side to another side, you have some transport phenomenon that makes that the information that you get out at the output of the network is a delayed version of what you get at some point. So I took this example just to say that if you send a sine, you have a delay of p over 2, you get a cosine at the end. Okay, and so it's something that is not very complicated, but you have to imagine that this may have some impact on the control and the stability of your system. You may also treat time quantization. So the trick is to say that you cannot send continuous data over the network. You have to send a sampled version of it, and this sampling may be time varying. Okay, so you may face this kind of situation in a lot of applications where you mix continuous time dynamics with discrete time controllers. Okay, so in this case, you may imagine this also very deteriorated situation where you have to send some cosine function, and you have a very bad sampling instance so that you lose all the information that is hidden inside the message. So the next one is space quantization. So you are also, due to the limitation of the bandwidth of your network, you may have to limit the information that is contained in the message. So what you do is instead of sending a number that has an infinite number, you have to design a finite language, a finite alphabet of values that can take the output of your network, and so you somehow quantized your message. Last part, which is more related to multi-agent system or consensus, is that maybe the message is the state of a set of multi-agent systems. So you have a very huge number of agents that are in place, and you do not have access to all the information of the state at all time. So you have to make some selection, and based on that, you need to do control, knowing just a partial information of your state. And so again, the objectives in this context are the evaluations, analysis, and the design method for dynamical systems subject to this kind of limitation. Okay, so this is a big picture of the work that I'm doing. And this also is a kind of a picture showing the effect of sampling, the work on infinite dimensional systems that I've been doing and that I will also present a bit in this presentation, the work on time delay system, and these more applicative applications of hybrid systems and multi-agent control. I will not go too much into the details, otherwise I will talk to you until 9. Okay, so this was a bit of the context of my research, and now I will go into the problem of time delay systems. So I will just, in this presentation, I will deal with this kind of systems that are driven by a differential equation where x of t is a vector. And these dynamics are defined by the evaluation of the vector x at time t, but also at time t minus h. So it's a delayed value of the state. And this kind of this kind of system, even though it is linear, very, very simple, you can see it in many applications, like in biology, robotics, and as I presented before, network control, and among many others. So in this presentation, I will only treat the case of constant A and AD matrices and constant delay, but I will show you how to deal with some things that are a bit more complicated. So to show that this class of systems are represented as a class of infinite dimensional systems, we just pick this very simple example, which is x dot is equal to minus x of t. And so when h is equal to 0, these dynamics converge exponentially to 0, like this. But as soon as you put some delay, you have this oscillatory dynamics that are appear. So even though this system is just a scalar system, the trajectories that you get are trajectories that have more than one pole, because these are trajectories where you have at least two complex poles. Okay. Another way to see it is that this system, when h is equal to pi over 2, you have two solutions to this class of system. And you know them perfectly, which are sine and cosine functions. And so what happens is that you see that sine and cosine functions are two solutions of these differential equations that cross at some points. And so this somehow contradicts the Cauchy theorem, which says that if two solutions of the differential equations are the same, so cross at some time, then they are the same all the time. So the trick is to say that the trajectory or the state of the system is not finite dimensional. It's just not x evaluated at time t. It's it's a function x considered over a window of time. And so another way to see that this class of systems are infinite dimensional is that if you look at the poles of this very simple equation, you can see that they have an infinite number of poles. Okay, so this is just to put in the context of infinite dimensional systems. And so this is the reason why in control it required this class of system required a dedicated attention and have been very popular over the 50 or 60 years. And more recently, there were a boom regarding this the treatment or the stability analysis of this class of system due to the emergence of what is called LMI, so linear matrix inequality, which are numerical tests that are very, very easy to implement and that are used, that are obtained by application of the so-called Lyapunov-Prasovsky theorem, which is an extension of the Lyapunov theorem, but to the case of time delay systems. And so why LMIs are very popular? So if you go back to the work of Lyapunov in the late 19th centuries, so he provided some very relevant theorem that was able to characterize the stability of a system only based on the study of its differential equation. And so he was able to obtain this kind of linear matrix inequalities where A are the dynamics of your system and is characterized by the dynamics of the system, and P is a Lyapunov matrix, and the P is a matrix that is positive definite. And so for a long time, the objective of people in control was to find the analytic expression of the matrix P that solves this kind of equations of inequalities. And it has a lot of impact, notably with the work of Yakubovich, Kalman, and Popov, which is summarized as the Kawai-P lemma, which makes some connections between the frequency criteria and the time domain approach. And what was very interesting in the 90s is that all the people in optimization were trying to solve linear semi-definite programming algorithm. And so they had this algorithm that was working very well, but without purpose application. and a good application where to use this algorithm. And actually, when control meet this optimization field, so there was literally a boom of use of LMIs in control. And it allows to have some numerical and results that guarantee stabilities without doing all this complex calculation of solutions of this kind of matrix inequalities. And so why LMIs are very useful? Because so they provide robustness to the stability. They are convex, and there are a lot of tools that are able to transform some nonlinear and bilinear problem into something that are very convex and very tractable. And they have the advantage to get some solution in polynomial time. So it's very convenient. Okay, so just to give you an example, I don't know if you are familiar with this topic of linear matrix inequality. So the basic theorem and the first one that are used is the following one. So if you consider a system that is driven by this ODE, you say that it is asymptotically stable, which means attractive and stable. If you can find some matrix P that are decision variables that verify this condition. And so it's the same but with a transpose matrix here. And so, of course, the stability of this equation is also related to the eigenvalues of the matrix A, and which has to be Hurwitz. And so just to explain the difference between what people were doing before, which was solving this, doing this kind of calculation, so obtaining an explicit definition of what is the matrix P that solves the Lyapunov equation. In our case, so we plug this in MATLAB, and MATLAB delivers numerical values for A and P. So of course, this is a very simple problem, but we can extend it to some much more complex problems that I will show afterwards. Okay, and so now let's go back to the problem of time delay system, and I will explain why this class of system have been widely studied in control. Because there is a methodology to develop stability criteria that is a priori to select a definite positive functional function of the Lyapunov function of the state of the system. To compute this derivative, to express it as a quadratic in the form of a quadratic expression like this. And so the LMIs refer to the sign of this matrix pi. Okay, which has to be positive definite. And the xi vector here is the vector that is collecting information about your time delay system. And so the objective of the people in control for a long time has been to derive less and less conservative stability condition. So why conservative? Because this is a finite dimensional test where xi has a given dimension, and you are testing that for infinite dimensional systems, which means that there are some gaps, and the objective of the people is to complete this gap. Okay. And the main problem is that there are a lot of degrees of freedom to define positive definite functional for your systems, depending on many terms. You can add some terms, and it has been a bit erratic for a while. And also, you can also see that you have a lot of degrees of freedom in the design of the xi vector that collect the information of your system. Again, we are thinking about time delay systems, which are infinite dimensional systems. So the idea is to understand what is the best vector xi that you are collecting there. So at the end, the question is how to choose good Lyapunov function and good vector xi so that you define the best and optimized element. And just for the joke, this is a joke that have been spread in control, where you can see this is the types of paper in control theory, and you have this yet another LMI approach, yet another paper on delay, and these are also theory papers that prove its superiority solely based on numerical academic examples. or yet another mix of compatible existing methods. And all these defaults are the defaults that you can see in this area. So it was very popular because it was easy to publish paper on these topics. So in this presentation, I will try to not fall in this gap. I will try to convince you there are some smart way and good ways to design LMI conditions for time delay systems and infinite dimensional systems. And this is how I will start. So first, I will try to work on the Lyapunov-Krasovsky functional and explain how it has been built. So if you look at the literature of time delay systems, for this linear case, so there is a generic form of Lyapunov-Krasovsky functional that has been derived. And this form is really the extension of what you have in the finite dimensional case, but then you need to add some cross terms between x evaluated time t and the state of the system. So x sub t is the value of the state over the window of time t and t minus h. And so this is a class of functionals that have been derived by Vladimir Kharitonov in the late 90s. And so the main problem, if you want to do numerical tests, is that you see that this is a matrix, but these are functions, and you need to define the functions and to be sure that they are differentiable and to find them numerically to have numerical tests. This is a complicated issue. But again, Kharitonov recently in Vladimir Kharitonov in 2012 provided a way to build explicitly the solution of so what is the structure of a good Lyapunov-Krasovsky function. And so it's a lot of equations, but I will just show you where it comes from. I will not detail where it comes from, but it's really the analogous of this calculus. So you define a matrix W so that this quantity is equal to 0 and this matrix W is positive. And so then what you do, you are going to integrate this equation and obtain this matrix P. So it's exactly the same. You can see here that you have the exponential 80 matrix, which is related to the fundamental matrix of the system. And again, this is a U matrix, which is a function, and this function is defined by this differential P. Okay. And so it might be complicated, but what is really interesting with this approach is that he is able to show that if your system is asymptotically stable, then you can build a Lyapunov function, and the Lyapunov function satisfies these conditions. Okay, and then this is exactly this. So if your time delay system is asymptotically stable, then this Lyapunov function is positive, and it is also negative definite by definition. Okay, and he even go further by saying that he was able to find an explicit expression of this function u. Again, I won't go into the detail of that because this is his work, but he has an explicit version of this. And from that, he was able to get some stability tests which says the following. So these are necessary conditions for stability. And you build some matrices that are expressed using this U matrix. You evaluate it at some points. So h over 2, 0, h over 2h, and so on. So you build this matrix this way. And if you find some cases where the matrix is unstable, not positive definite, this implies that your system is unstable. Okay, so it's a test that allows and he was even able to go further in the work of Sabine Mondier and Egorov to have if and only if condition for the stability, where actually you evaluate the order of the matrix that you have to build. Okay. So this was just an introduction to this idea. So it was just to say that for a linear time delay system where you know the matrix, when you know the delay, you know how to build Lyapunov-Krasovsky functionals that are necessary and sufficient. And the work of and the team of Kharitonov, Mondier, and Egorov applied and extended to various classes of delay system. So if for systems where you have multiple delays, distributed delays are where you have kernels. I think that you called it memory terms, and neutral delay system, but I won't go too much into that. And the main issue is that you do not have robustness for this class of systems. So with this criteria, which means that if you have some uncertainty in the A and AD matrix or in the delay, in the value of the delay, it does not work anymore. So this is why we would like to have a similar study that is based on LMI that includes robustness, and we would like to understand if we can get some LMI conditions that are necessary and sufficient as well. So let's go back to LMI. And instead of working on this very complicated Lyapunov-Krasovsky functional, we go back to the work of Emilia Friedman in 2002, where she introduced this very simple term. Okay, so it's a Lyapunov function that is parameterized by three matrices, P, S, and R. And I will show you why it was very interesting at the time, is that when you compute this derivative of the Lyapunov function, you can express it like this, but with this term here, okay? And so here, our objective is to express this derivative as a quadratic term, depending on some vector psi that characterize the stability, the state of your system. The issue is that this function is a bit complicated to treat and cannot enter directly into the framework of LMI. So what you have to do, you have to apply what we call in control Jensen inequality, but it is actually Cauchy-Schwarz, to give a lower bound of this integral, and so that we can apply it. Okay, so how it works? This is this lemma, Jensen inequality, so it is, again, Cauchy-Schwarz. And why is it interesting is that you are able to find a lower bound of this term here, this quadratic term, that is expressed using quadratic expression. And so it was very popular in our area, mainly because this quantity depends on the value of the delay. And so the stability test that we get depends on the value of the delay. And so we are able to characterize the stability of systems whose stability may depend on the delay. And so this is what is called delay-dependent stability condition. But it was not enough, because this inequality introduced conservatism. Conservatism means that you are losing a lot of information of your system when you are applying it. If you know a bit about robust control, so the fact that you are using this inequality can be translated into having an uncertainty to your system, and this uncertainty is the blue area here, and you are overestimating this uncertainty, and you are bounding this. You are bounding the uncertainty in this circle here. Okay, so this is just a figure to explain that when you apply Jensen inequality, you are losing too much inequality. So there is a room for improvement. And so how do we do? So first, we had to understand that Jensen inequality was indeed Cauchy-Schwarz inequality, and Cauchy-Schwarz inequality is obtained by calculating this kind of square matrices, this square expression. Okay, so what you can see is that it's a square because these terms are the same. R is a positive definite matrix, So you just have to expand this expression, and you see that the cross products are equal to this quantity, and you have it twice, minus twice here, and you have the double the square of this of these two terms that are also in the same. Okay, so this is something given. And so we did a first try, which was to the objective was to find a lower bound of this integral of this integral of the error, which was based on Wertinger inequality. And just to tell you that that it was something that was not being visited in this area, is that we published this paper in 2013. And today it has like 2,500 citations in this context. Again, this is just because there are a lot of people that are working on this area and that are publishing a lot incremental results. Okay, and I will not talk about that, but I will show you that we can do much better by using Bessel inequality, which are some limited version of Parseval identity. And let's see how it works. And so the main idea is to say that this inequality can be interpreted in the term of if you introduce the scalar the inner product, which is the integral of two functions here. And so you can integrate, you can rewrite this integral E as the error of a function considered over the interval minus its projection respect to the vector of 1. Okay, so the set of constant function. Okay, so actually when we are using this Jensen inequality, what we are doing, we are approximating a function by its average. Okay, but actually we know that we can expand this inequality to a wider class of function bases, and actually as soon as you get an orthogonal basis of your set of function, you can derive more and more accurate expression. And this is what we did by using this the orthogonal polynomial of Legendre, which are well characterized for the inner product that I considered before. And so this inequalities is written like this. So now you have not only one term, but a set of diagonal matrix composed of diagonal blocks that are all depending on this R matrix here. And you have these blue terms, omega 0, omega n, which are projections of your state x, or the function x, over the set, the basis of Legendre polynomial. And the proof is very easy, and it takes 2 lines, because it's just to compare the function x and to compare it with its projection or its approximation, its expression given on the basis of orthogonal polynomial. And so you get this expression, which can be written like this. So why was it interesting? Why it is interesting, and what can we say? So first, it is optimal in the sense that when you are using orthogonal polynomial, you are doing optimization. So you cannot do better. There are a lot of people in control that are using free weighting matrices or like introducing some degrees of freedom. But the fact that we are using orthogonal basis just shows us that it is the best. And it is the best because it is a unique polynomial of degree less than n and minimize the distance between the function x and the set of polynomials with respect to this inner product. Okay, you can see several other versions or extensions in the literature where a similar paper was published by some Korean colleagues, which was just considering the case n equal 3. You have some other people that are using the canonical basis here instead of Legendre, so they had to compute the grammar matrix. So these colleagues from China did also some things related to any independent set of independent functions, or people that are using Jacobi polynomials for multiple integral inequalities. We did something on a discrete time version where you have discrete time dynamics. And you can also imagine that you have integrals over infinite supports, so which means that you have to consider the long history to minus infinity. Okay. So some relevant cases. So if you pick n is equal to 2, you recover the Jensen inequality or the Cauchy-Schwarz inequality. And the first, so the Wirtinger-Bayes inequality, which is the one that I told you about before, are the very first case. Then you have Parseval identity that tells you that if the number of projection goes to infinity, you have equality between the integral and the infinite sum. And you have something more, which is related to polynomial approximation, and the fact that if your function is sufficiently differentiable, you can prove that the Legendre approximation series converges uniformly to its generator. In other words, for all bound epsilon, there exists some value of n that depends of epsilon, such that for all the n greater than the n epsilon, and for all the s in the interval, that your function is uniformly bounded. The error between your function and your polynomial approximation is bounded uniformly. And so this is just to say that after some steps, you have the F3 that coincides very well with this. Okay, so now let's understand how do we do that with control and with our LMI tests. And so our LMI test is very simple. It is written like this with a very diagonal structure. So you have these diagonal matrices that are really related to the Bessel inequality. These are matrices that I do not want to detail because it's not very interesting, but it's something that depends on the structure of the systems, depends on the properties of Legendre polynomials, on the derivative, on the formula for the derivation of Legendre polynomials. But what is really interesting is that you have the structure that is given by the Bessel inequality that is here. And so basically what we say that now if you, for a given n, you can find solutions to this matrix linear inequalities, where Pn is a big matrix. So this matrix is of the size of the system multiplied by the number of projection plus 1. Okay? And so if you can find some solution, then your system is asymptotically stable. So it's a sufficient stability condition for your time delay system. How do you do the proof? The proof tells you, and the Bessel inequality tells you what is a good Lyapunov function and how to build it. And how to build it, it is very simple compared to what I showed you before, because it is just a quadratic term that contains the x of t, the current value of x, plus all the projections. And so what was very fascinating at the time is that when you compute the derivative of the Lyapunov function, you have to compute the derivative of the projection. And doing integration by parts, you have to use the recursive expression for the derivative of Legendre polynomials, which simplifies a lot the calculation. And you can really have a structure and define this function, this matrix here, for any value of n. So it's very well constructed, very well defined. And so you take this functional, you compute this derivative, you apply the Bessel-Legendre inequality, and you get a stability condition for the based on the application of the Lyapunov-Krasovsky theorem. So what can we say now about robustness? These conditions are convex with respect to the matrix of the system A and AD. Again, I did not show what is inside, but trust me, so which means that you can have a numerical test for matrix A and B that are bounded, that belongs to some convex set. Okay, so this condition is also convex with respect to H, which means that if you have a solution to this these LMIs for a given H, So this, which means that you have a solution, numerical solution Pn, S, and R for your system, and you try to verify that it is still positive and negative with the same matrix Pn, S and R for different values of the delay. If it's true, then it means that your system will be stable for all the value of the delay that are between this interval. So it's convex with respect to H. In terms of complexity, so it's a numerical test, so you have to verify that your test is not very complex. So what do? Each time you increase n to n plus 1, your matrix Pn, which is the only one that changed, increase by one row and one column, and so the number of decision variable is quite contained, and the size of the decision of the LMI is also contained. And this is how you control the complexity of the linear matrix inequality. And this, the simplicity of the Lyapunov function, the simplicity of the test makes it very competitive with respect to many kinds of stability criteria that were used at the time, which are based on discretization or sum of squares or multiple integrals method and so on. So now, question is, what happened when we go from n to n plus 1? And this is, for that, we have this theorem, which says that this LMI forms a hierarchy of LMI conditions. So to say it in this form, so if you have a solution to this LMI as an order n for a value h, it implies that it's the same LMI at order n plus 1 will be also satisfied. Again, this means that each time you increase n to n plus 1, you are just allowed to increase the set of delay for which you can guarantee stability. This result strongly relies on the fact that when you compute this matrix here, you make the derivative. At some point, you need to use the derivative of the Legendre polynomial, and what you have is that the derivative of a polynomial is a polynomial of degree lower degree. And this is the fact that makes that this fact that makes the LMIs have a hierarchy. So now we have to understand if we gain a lot each time we increase n to n plus 1, and so to do that we apply it to some example. So it's not a simple example. So it's 4x4 dynamics. We have some delay, and so we have two parameters. We have a parameter k, which is a control gain, and the delay h. And so what you can see here, it's a plot that evaluates the delay for which we can find solution to this condition, and the control gain k. This black area here is area for which we can use frequency analysis to understand if the system is stable or unstable. And so what you can see here is that for different values of n, for instance, you have n equals 0, n equal 1, n equal 2, and so on and so forth. Here you have n equal to 5, 6, 7. And so each time you increase n, you may increase a little bit here, and you may sometimes increase a lot. So you gain a lot to get a stability region. And so somehow it gives the impression that you are blowing a balloon from the stable region to reach and to cover all the area of the stability region. Okay? And so last step is about the convergence. So you want to know if, so let's go back here. So here, this set Hn are the colored set that are here. And so we would like to understand if when n goes to infinity, the set of solutions for which we have, for the sets of delay for which we have a solution to our LMI is exactly the white area. Okay, so convergence of the LMI condition. And so this is something that we did with my PhD student in Toulouse. I must admit that at some point I was a bit hopeless to find a solution to this problem, and this guy was just amazing and came with a solution. So this is how it works. So you start from the complete Lyapunov-Krasovsky functional that I showed at the very beginning of the presentation. The one that says that if the system is asymptotically stable, then you can build this Lyapunov-Krasovsky function. Okay. So then the second step is that you know that this function is defined using a U matrix for which you have an explicit solution of it. And so you can build a polynomial approximation of this function U, and you express it using the Legendre polynomials. As a next step, you compute the approximation error between the two functions. So the V approximated based on the Legendre part and the one that is necessary and sufficient. And you have these error terms here. Then you use the uniform convergence of the Legendre series of this function U to show that these two functionals are uniformly bounded, and which means that when n goes to 0, you can bound these two terms uniformly. And as a last part, because our conditions are LMI, you need to verify that the resulting matrix that you are building is positive definite. And so to do that, you have to express this function. You have to consider some set of functions for which you can prove that the LMI condition is necessary. And so this is just a sketch of the proof of how we prove the convergence of our sufficient conditions. And we can, yeah.
Alex, I'm sorry, we are running out of time. 3 minutes. Can you?
Okay, 3 minutes. So maybe
More or
I will
less.
stop.
Yes.
Okay,
Thank you.
I will go there. So we went also to the case of necessary and sufficient condition, because we are able to find an estimation of what is a good order. Okay, let me just skip that and show this part, which is probably more related to what you do. So recently we have seen the work of Miroslav Kristich on Smith predictor, and backstepping approach for a system with input delay. And so to do his approach of backstepping, what he did a model transformation, which consists in writing this time delay system as an interconnection between an ODE and a transport PD. Okay, and so the ODE is fed by the output of the PD, and the PD is fed by the input of the ODE, by the output of the ODE. And so the idea was to say, okay, let's go and try to apply this method to this case, to this class of system. And so we were able to extend this work to the case of ODE equation translated to interconnected to transport PD with various transitions. So the method is exactly the same. We define a Lyapunov function based on projections, and this term, which is a Lyapunov function for the transport equation. And so we apply the same techniques, and it has an impact which says that we were able to define very simply criteria for system with multiple delays or cross-talking delays, where you have two delays. And I will stop here. So we also extended to various class of PDs. And so the technique is the same, is that you have, for instance, here the heat equation or the wave equation. You know that there are some Lyapunov function for the heat equation and for the wave equation. And you apply the same technique by augmenting the vector x tilde, and you can get stability tests for this class of systems. Okay, and this is just what I wanted to show, and I will just stop here, if it's okay. Otherwise, I will be too.
Yes, okay. Yes, it's okay. Thank you, Alex. Thank you very much for your talk. And it has been very interesting. We will give the opportunity to the audience if they want to ask something. or make some comments. They have they can talk in the micro or write in the chat. So anyone has any question or comment?
So thanks for attending for the European people that late and that
Yes,
early for the Brazilian people.
yes. So I will make a question. First, thank you for all the presentation. It was interesting also the introduction that you have done in the beginning in order to state all the context and
Mhm.
where you come from, no, for all the studies and research that you have done. And it seems to be a research area that has a lot of knowledge, no, and a long career studying these kind of topics, no. It's not, it can be
So
seen in the results that
you,
there are many work behind this.
no, it's a bit of summary of what I've done with my colleagues
Ah,
in Toulouse. So you probably know Lucie Baudouin.
yes, I know her.
Okay, and so she's one people that helped me to make this transition between what I was doing in time delay system
Ah,
to the PD, and this was really interesting to know a bit more. And
yeah.
indeed, this is a kind of summary of let's say 10 years of work.
Yes, 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 yes. It can be appreciated in the presentation. And yes, and it has been very clear also the presentation. And one question that I have, because I don't know almost anything about this, but you mentioned at some point in your presentation that you wrote one question, how to choose a good Lyapunov function and a vector size, no? And
Mm,
I think that with the ideas that I have, it doesn't have to be easy, no, to choose the appropriate Lyapunov
ex-
function, no,
ex-
depending on the context or.
Exactly. So the problem was that people were just proposing, let's take this one,
Yes.
let's take this one, let's take this one. And so what we found with actually with Frederick is that this inequality, which is like Bessel inequality or Parseval, which is something that is very well known, drive us to find the best and the good solution to
Oh.
find the best vector. So, and so numerically, it's impressive how
Mm.
fast it works
So
compared to what.
so the Bessel functions help you to choose the best one.
Yeah, exactly,
Yes,
exactly.
that's a good method. Mm. Yeah, so thank you. Does anyone has any question in the audience? If not, we thank you again. Thank you for
Okay,
giving your talk.
thank
Yeah,
you for
it
listening.
was a pleasure. And